Hi, okay, so now I'll be going over estimating a proportion. So, say that we have a series of independent and identically distributed Bernoulli random variables. And so, in this case, our sample proportion will be equal to the sample average of the number of successes. And so it's basically the same as the sample mean in this kind of distribution. So using the central limit theorem, our statistic, which is our population proportion, P, is asymptotically normally distributed with our mean. So essentially we can use a formula that's very similar to our previous formulas for estimating the mean, the population mean, except we're estimating the population proportion. And here we can see that the mean is P and the variance is P times 1 minus P divided by N. And so we can come up with our test statistic, which is down here, where our test statistics should be between negative z alpha divided by 2 and z alpha divided by 2. Yeah. So when n is large and little error is introduced, we can use the point estimate to estimate the variance of p for our population. And we can use this formula that we had earlier. If we just rearrange some of it, we can come up with this formula over here, and that's how we can find the confidence interval of our proportion for our population for our using our alpha value. So our confidence level would be the percent of 1 minus the alpha value times 100. And we can use this formula to find our confidence interval. And then just a note is that we need to make sure that both our n times p and our n times 1 minus p are both greater than or equal to 5, because if they're small or unknown, then our confidence interval isn't going to be very accurate, so we can use other methods. Okay, so let's go through an example. Okay, so in a random sample of n equals 500 families owning television sets in the city of Hamilton, Canada, it is found that 340 subscribe to HBO. We want to find a 95% confidence interval for the actual proportion of families with television sets in the city that subscribe to HBO. So, what we need to do, so first we can find our p-value. So our proportion for our sample is given over here. So out of 500 we have 340, so that would just be 340 divided by 500, which is equal to 0.68. And then we're looking for a 95% confidence interval, so this means that our alpha value is 0.05, because for our 95 confidence interval, 1 minus 0.05 is 0.95. Okay, and then so now we can use our formula over here. So we already have our p, And so now we can find z alpha divided by 2. And if we look at our z table, what we should get is, so it should be 0.025. So if we look through our z table, we can find the value of this, and that should be 1.96. And then now we can plug it into our confidence interval. So we can have our 0.68, so that's our p, and then we have minus 1.96, and then square root of 0.68 times 1 minus 0.68 divided by n, which is 500. And then we have same thing here, except we add. So 0.68 plus 1.96 square root 0.68 times 1 minus 0.68 divided by 500. And then if we solve this, we should get 0.64 and 0.72 as bounds for our confidence interval. And so now we can say that we are 95% confident that the true proportions, this is the population proportion, is between 0.64 and 0.72. Okay. And then we can also do testing with our proportions. So we can calculate the test statistic using z again. So for proportions, this is the formula over here. And then we can do the same thing with the hypotheses, where the null hypothesis is where p equals this value, and then alternate can be if it's not equal to it, if it's greater than or less than. And then we have the different scenarios for if we reject, based on if it's one-tailed or two tails and which tail it is. And then another note again is when n is small, or when p0 is close to 0 or 1, we shouldn't really use this test because it isn't that accurate. And then our exact p-values can be calculated since x is a discrete binomial random variable, and so this is useful for when samples are small. But for larger sample sizes, the computational costs might make us need to approximate our mean and p-value for our proportions, and we can use normal approximation for that. Okay, so another example. Okay, so commonly prescribed drugs for relieving nervous tension is believed to only be 60% effective. Experimental results with a new drug administered to a random sample of 100 adults who were suffering from nervous tension showed that 70 received relief. Is this sufficient evidence to conclude that the new drug is superior to the one commonly prescribed? Okay, so first, as with all tests, we want to make our null hypothesis and our alternate hypothesis. So our null hypothesis is that p is equal to 0.6, since we're believing that it's 60% effective. And then our alternate hypothesis is going to be that p is greater than 0.6. And this is because we're trying to find out if the new drug is better than 60% effectiveness, and that's why we want greater than 0.6 instead of not equals to or less than. Okay, and then now we can calculate our z statistic. So we can use our formula over there. So our probability, so first we can calculate our proportion for our sample. So it says that we have 70 divided by 100, so we have 70 that received relief over n is 100 for the total sample. So that's 0.7. So now we can use that. And then minus our p0, so that's 0.6. And then we can plug in our values, so 0.6 times 1 minus 0.6. And then all of this is divided by our n, which in this case is 100. And so if we solve that, that's about 2.04. And then we can find the probability that z is greater than 2.04. And then we can use our z table again. And if we just look up that value for z and make sure that we're doing the tail to the right, not to the left, because it's z is greater than this instead of z is less than. We should get the value 0.021, and then this is less than our significance value. Oh, I almost forgot to mention, but we should be using, if it's not mentioned in the problem, usually you'll be using 0.05 as our significance value. So since this is less than our significance value, we can reject our null hypothesis and conclude that the new drug, there's significant evidence that the new drug is better. And that's all. Thank you for watching.